Hey guys, it's Tyler from CG Forge. Lately I was working on Destruction 2 and I wanted to share this first 3 lessons with you all that gets into the basics of Sop-Level RBD tools. This was released with Houdini 18 and it's really cool because it makes a lot of tasks very convenient. Now, if you're somebody who's never done any RBD before, I would recommend checking out my course Destruction 1 first, because that goes over the basic concepts and terminology. But assuming that you already understand some of the basics, this is a great tutorial or series of lessons to get you started with those SOP level tools. Also, if you're subscribed to CG Forge, then you can get the scene files that you see right here to start playing around and practicing before the rest of this course is published. I hope you guys enjoy. To get us started with the RBD SOP tools, go ahead and press Tab and type in RBD. Most of the nodes that you'll need start with RBD, and so whenever you're working with these SOP level things, just remember that you type that in and you'll find most of the nodes that you need to make everything in this particular workflow. So the first one you need to figure out is the RBD material fracture node. And this is responsible for setting up the fracture geo, constraints, as well as proxy geometry, which I'll talk about in a little bit. But for right now, let's just plug that into this Greeble 9. And what we'll find here, if I use an exploded view, is that we have all these Voronoi fractured pieces. So pretty cool. But what's cool about this RBD material fracture node is that we have different presets. So if we go towards the top here, right now I'm at concrete, which is that Voronoi shape, but I can also go to glass, wood, and custom. So with glass, if I use this preset and use an exploded view, we have a very different results. And likewise with the wood. And depending on which one you pick, it's like having a completely different destruction workflow with one option that you toggle. So I guess if you were to generalize all these different things, you could say that the concrete gives you that chunky Voronoi shape. The wood gives you these wood-like shards or anything that's really elongated. And that glass is great for anything with a radial centric sort of shape. Okay, so we know that there's 3 different workflows happening within this node. We can actually dive in by pressing enter and look at all this. It looks very scary, but remember, this represents 3 different workflows, and it's setting up constraints, and it's also creating proxy geo. So don't worry yourself too much if this looks a little bit scary and confusing. You don't really need to know all this. And that's kind of the beauty of this RBD system, is that it's very high level, and it's meant to save you time so that you don't have to go through these setups manually every single time you want to make something blow up. So there's that. Now, to start off here, we have this concrete preset. And what's happening under the hood is essentially this. Say that I just create your standard Voronoi fracture. We scatter some points, maybe like 20 of them. We type in Voronoi fracture. There's the geo, there's the points. And we end up with that, which again correlates with where those points were scattered. We have 20 points, that gives us 20 pieces. The point exists in the middle of each piece. All right, well, that's all cool, but what's happening here is that we're using a Voronoi fracture on top of additional Voronoi fractures. So it's kind of like doing this, making a duplicate over here, and then scattering on the fracture and doing a Voronoi fracture on top of a Voronoi fracture. So now if we did this, we end up with more pieces based on these new additional scatters. So that's what's happening here with this concrete preset. And if we go to the primary fracture tab, that relates to this 1 and 2 tab. The 1 represents the first fracture that happens, and the 2 represents the second. And as you can imagine, you can keep on adding more of these fractures for as much as you like. So We can do 3 rounds of Voronoi or 4 rounds. It's totally up to you. What I like to do in this case is I like to start off with just one fracture. So let's go back over here, and we have one fracture. Let's go down here, change the scatter points to maybe like 10. So I want 10 pieces. And, well, there you go. There's 10 pieces right there. But watch what happens when I press this plus icon. As you can imagine, we scatter points on that fractured geometry. So now we have 2 layers. But here's what you have to be careful about. If I go to the second tab and I look at the scattered points, look at that. We have 10 points. And this is supposed to represent the second round of Voronoi fracture. So what that means is that as you add these layers, it's not going to add them properly. In other words, tab 1 is now tab 2. It's no longer my base layer that I pictured in my head. Also, this fracture ID doesn't get updated properly either. So this fracture ID basically keeps track of the particular fracture that you're on. And it does this through the output attributes and groups associated with this particular fracture. So in other words, it's like tagging the information for what that fracture did. And like I just said, the fracture ID isn't properly named whenever you add a new layer. So what that means is that we need to work around this current limitation. This actually might be fixed in a future release, by the way. But for now, just to keep ourselves organized, let's start off by renaming this fracture ID. And so for the second fracture, we'll say concrete fracture 2. And then let's also set up our scatter points to begin with 10. That's our base layer. And for now, on the second layer, I'm just going to say 5. So we start off with about 10 pieces, and then we go to about 5 pieces for every single piece that we had before. So now that we do this, and we change this to auto update at the bottom, now we have about 55-ish pieces or so. The scatter points, by the way, aren't going to give you a precise number of pieces, but it'll get you very close to that number of pieces. So here we have about 55 pieces. Again, that's because we started with 11 or so, and then we had 5 pieces break off of every single piece that was there before. Okay, so we have that going on. Now, we also have this fracture ratio, which determines how many pieces of the previous fracture you are allowed to fracture on. So for the second layer here, let's say that I don't want to scatter 5 points on each individual piece. I want there to be a 50% chance that that happens. That's what the fracture ratio does. So if we say 0.5, again, 50% chance that we are able to scatter these points onto a piece. Now we're left with some of these bigger chunks along with some of these smaller ones that just got broken up. So to really see this, let's take our scatter points from 5 to, let's say, 40. And there you go. Now you can really see this exaggerated quite a bit. It picked that one piece and it chose to scatter all the points, about 50 or so points, onto that one piece. So that means we can get variety through this fracture ratio. But here's the confusing part. You'll notice that we just said 50%, but only one of these pieces got fractured. And if I change the seed, well, it's just not very consistent. Sometimes only one piece gets the 50% likelihood. Sometimes other pieces, sometimes nearly everything, like you just saw right there, is going to get the scattered thing. And that's because this is just a probability that that's going to happen. And on top of that, we have this thing down here called the fog volume, which will mask off where those points are allowed to scatter as well. And so what that means in practice is that we have a ratio here of, let's say, 50%. And even though you say 50%, you really have to play with the seed to make sure that it's giving you the result that you expect. So as you're working, if you want to make sure that this is happening only about half the time, play around with the seed until you see that happening, and then just leave it alone. So here I see that, all right, well, about half of these pieces are actually being shattered now. I'm going to go down here and change this back to 5, and there we go. Okay, so that's all cool. And now if we go to add a third, what you'll find is, again, we have this issue where it's not going to sort our tabs properly. So this is probably the most frustrating thing about this node. Again, I really hope that side effects cleans this up a little bit. But this all goes to say that when you go to fracture this stuff, you also want to have an idea of how many layers of fracturing you want to do before you start dialing in these settings. Because now fracture 3 was what fracture 2 used to be. Fracture 2 is the default. Fracture 1 was left alone. Again, it's all kind of a mess here now. So let's just leave this at fracture 3. And for right now, let's just turn off those scattered points. I'm going to get the second layer here dialed in at about 50% as well. So I'll say 0.5 just to see what we're doing. 20 points. And then I'll mess around with the seed until we have about half these things actually shattering like that. Bring back down the scattered points to, let's say, 10. And now I have a situation where this 0.5 is somewhat representative of what's happening, and we're left with big pieces, mid-sized pieces, and small pieces, which all come together to form a much more interesting fracture. In the next video, let's talk about constraints. I'll show you a few more things about this whole primary fracture section, and then I'll also talk about proxy geo. So before moving on to the constraints, let's talk a bit more about this primary fracture and how that works. We mentioned that we can control how many points are being scattered right here, but the distribution of those points depends on a fog volume by default. And so if we go here to this guide geometry and we select primary volume, that will give us a visualization of that fog volume. And wherever the value is 1, that's where we see red. That's where points will scatter. And the black areas say that points are less likely to be in those areas. So if I change this to something else, let's say we take the frequency down so that we have a pretty big shape, and we change this offset, maybe like right about there, so that we're just concentrated towards the bottom. If I set the scattered points now to 100, and we take a look at this, as you can see, because those values were 1 towards the bottom, that's where the 100 points end up spawning. And if we middle mouse, we have about 100 pieces. This 100, by the way, doesn't always give you exactly 100 pieces, but that'll give you about that number. Okay, so that's one way we can control where this goes. There's another way we can do that as well. And if you don't want to rely on this fog volume, instead, we can go to the section right here. It says scatter from, and change that to attributes. So now, instead of looking at the volume, that's all gone. We need to create an attribute before this RBD material fracture to say where the points are allowed to scatter. So let's create an attribute paint for that. Right there. And if we go to attributes, say density. Now I want to have these points scatter, let's say, towards the top right here. So I only want it to break off in these areas. Okay, so we do that. We said scatter 100 points. We said look for density. And now, as you can see, we've controlled it by doing that. Now, there's another way of doing this. And instead of making this attribute paint right here, we can just scatter the points ourselves if we'd like. So if we just say scatter right there, and let's just say that we take this attribute paint and do the same kind of thing. So we scatter We check on density so that it only scatters points in those areas. And let's just turn this down, maybe like 100 points or so, and turn off relax iterations so that it doesn't evenly space everything. Now we can plug this into the fourth input, like that, and we don't need this guy. And if we go, say scatter from volume, let's turn this off so that we can keep track of what we're doing. So say none on fog volume. And now if we go to this input points, we check that on, and we're now listening to the fourth input, which are the points we just scattered. And that gets added on top of whatever this RBD material fracture wants to do. So now we have extra pieces happening up here. If we middle mouse, we end up with around 200. That's about 100 from here and about 100 coming from here. I suppose the reason why you might want to use this input points is if you have a group of points that you'd like to refer to. The problem with doing this attrib paint up here is that you can't take groups of points and adaptively bring that in, but you can do that with this input points and specifying a group. So that's why we have that right there. Now you should also be aware that we have this thing here called scaling, and I haven't found any reference to this in the user docs. So quite frankly, your guess might be as good as mine when it comes to this sort of thing. My recommendation is to leave this alone unless you somehow know what this means. Also, in general, as far as a good workflow is concerned, I like going with this scatter on the fourth input. I've just found it to be a lot more predictable, and I know exactly where those points are going to be, and I can control that separately from the RBD material fracture node. So I kind of like going this route, but if you want an area with a specific concentration of points, you can do so by painting this out, and also with each layer, you can just source different things. So let's say that we want to have a different group of points that we refer to on the second layer. We can do so by specifying a group, and that's how we can control where something might scatter on, let's say, the base layer. Then on the second time it goes to do all the fractures, then the third time, and so on and so forth. So really, this is a great way of just breaking up the shapes, getting something that's interesting and different, and something that's not the default chunky business that you see right here. Meanwhile, at the Geo spreadsheet, we have all kinds of fun things happening. For one, we have a nice assortment of groups which keep track of the pieces, where they are, if they're on the outside of the mesh or the inside, as well as this fracture ID that we mentioned right here. So that's good to keep track of that. Most importantly, though, is this name attribute. So we start off with this piece, which right now is just piece 0. And if I go down, piece 0 is basically just the name that it gave this greeble right here. Because we didn't have a name going in, it just said piece 0. But to change that, we can say name, and we can give it any name we want. So let's just say everything now has a name of Mr. Greeble right there. So now, Mr. Greeble, that's the model coming in. Dash, this is the fracture. So this is the first fracture that we have, this first number. So index number 0, it starts, and then it goes up from there. And then right now I have 2 levels. So the second level right here is the next dash. And so this is taking from piece 1, and this is, let's say, number 4 of piece 1. And then that's keeping track of which piece this is. So we have all that going on. The reason why it's not just one primitive per chunky piece is because the inside pieces are not necessarily attached to the geometry out here. If we do a wireframe, we can really see that we have 1, 2, 3, 4, 5 primitives that make up that one piece. And so that's why we have that going on. But anyway, I just wanted to show you real quick what's happening in the geo spreadsheet. Another thing to keep in mind is that if we want to change the geo stream, we can go right here and change that. So this is the geo. We can say constraints, and here's all the attributes for constraints, and then likewise with the proxy geo with that tab. Now, speaking of constraints, we have that tab right here called constraints, which sets up all of the default properties for what we want to do. So if you want glue constraints, you can say that right there. We can also, let's say, enable color. That's really fun. Let's choose maybe red so that we can see it really well. And, well, it's going to be kind of difficult to see this in the viewport, but one way you can do that is by creating a null and just plugging that into, let's say, this second input. So there we go. Now we have a color, that red color, for the constraints. Or, we could do green or whatever you want to do. The nice thing about that color is that it helps you keep track of the different constraints. So if, let's say, for glue constraints, you always made that blue, well, that's a very nice way of visually keeping track of where your glue constraints are versus your soft or your hard constraints. So anyway, we have that. We have the primary strength. It's the value that starts at level multiplier and strength variance. So all this kind of stuff relates to setting up the constraints. One last thing I do want to show you, though, before we wrap up this video, is the proxy geo and what's going on there. The whole idea behind this is that the proxy geo is going to be the geometry that the solver uses to figure out the location of everything. And the reason why we separate that geometry is because if we make this geometry less polygons, then we can sim much faster. And as long as we retain the shape, then we can just use that to control the movement and then apply that movement to the high-res pieces. So if you want to have this set up automatically for you, you can go to Detail, and at the very bottom, we have this proxy geo, and you can set that to either convex decomposition or packed spheres. This convex decomposition is basically using the shrink wrap node to create low-res versions of everything. So this is pretty cool. Low-res versions, it has the same shape. It'll simulate just fine. But compare this to, let's say, how many polygons are being used here. And you can see why this geometry right here is going to be much friendlier when Bullet goes to sim everything. We also have packed spheres, and with this whole idea, we're trying to represent the geometry with these tiny little spheres. And these spheres are able to simulate really quickly. And so this uses this voxel size that we can dial in, and the lower you go with this voxel size, the more accurate this representation is going to be. So a voxel size of, let's say, 0.05 might be pretty good. And we also want to keep track of how big they are with this min and max radius. So for now, let's just say it's 1 and 8 like that. And if we go to our exploded view and we bring this all back, as you can see, we have a somewhat decent representation of all these pieces. And again, we're using all these spheres. Specifically, it's actually the primitive type is called a sphere to make these collisions. So it's pretty cool. But you might have to play around with it to see if this really works out well for you or not. I guess my generalized advice when it comes to this is that if you have pieces which aren't really making contact with the ground and you don't really see them settle down, then the spheres could be a very fast way of simulating, and you might want to consider this. But otherwise, for most situations, this convex decomposition is probably what you want to use on most occasions. We also have this max concavity, and basically puts, if you add detail to the edges through this little edge detail thing, which, since we're here, I'll just show you that. So I check on edge detail, and it goes really slow, but we now have this wavy business happening along the edges. This max decomposition basically takes a look at these edges and it tries to figure out at what point has this gotten too wavy that I need to make another piece. So now, if let's say I go over here, there is the proxy geo. And as you can see, it made two pieces like that. One right here, one right here, because it detected that inward slope. And it did that through, again, the max concavity option right here. All right, so that's that. I think we've talked enough about this RBD material fracture for now. In the next video, let's actually throw this into a bullet solver and make stuff happen. So let's say that you're happy with this fracture right here. Let's now move on to the RBD bullet solver. And this is just a DOP-net. It's really just a nice collection of presets that you would go through whenever setting up a DOP-net for a RBD bullet solve. So we plug that in there. Again, geometry, constraints, and proxy. And, well, by default, everything kind of just has some gravity, and it just goes like that. But what's nice about this is that we have all these options here to enable, let's say, a ground plane with one click. So the reason why you would use this bullet solve instead of just making it yourself is because of the convenience of some of these options, just like we did with the ground plane. Now, if we go in here, you'll notice that we don't end up at the DOP level. We end up at this forces subnet. And basically, this is feeding into the pre-solve of the rigid body solver. But to actually see the DOP-net and where this is happening, we need to go up one level right here. And this is essentially the simulation that we're dealing with. So here's the bullet RBD solver. Again, the pre-solve right here is where we can feed in those pop forces. So that's this guy right here. And then we just have a bunch of other nodes that we can turn on if we want to, let's say, conveniently add drag or drag spin or things that are commonly associated with an RBD solve. So let's go ahead and go back here. And again, we want to just say the ground plane right there. And for the forces, let's also add a drag and drag spin. The nice thing is that these defaults actually relate to the measured real-world drag and spin that you would typically have for objects as they move through air. So you don't really have to guess that. So now if we go forward a few frames, nothing's going to happen. And that's because we have our glue constraints. They're set to a high value and they're not crumbling because of gravity because they're strong enough to resist that. But if we do want this to crumble based on gravity, we can just turn that glue strength down to, let's say, a value of 1, and then we can go forward and see this crumble like so. So now we have that. Let's take a look at what's feeding into this RBD bullet solve. Create a null and go to the primary geo. If we middle mouse, you'll notice that we have polygons, and these are not packed primitives. As I mentioned in my course Destruction 1, we want, in most situations, packed primitives or packed fragments whenever we go to simulate this stuff. And so by default, if you just go straight from the material fracture to the RBD bullet solve, you're left with 40,000 polygons, and that's not good. Likewise with the proxy. Here we have 5,000 polygons, and the reason why there's a difference there is because of the edge detail. So here is the proxy. We don't have any of those wavy edges. As I feed in the main geo, we now have all this detail, and that's why it's 40,000 versus 5. Okay, so we just mentioned that we don't have packed fragments going in. To do that, say RBD configure. And this is something that you want to set up anytime you go into the RBD bullet solve. So let's go ahead and situate that right there. And this RBD configure is great because it lets you specify all sorts of attributes that you might want to source into the DOP sim. So in the past, I've mentioned that we need to be sure that we take a look at the attributes on the pieces before they hit the solver. And the nice thing about this RBD configure is that it does a lot of that automatically for you. So if we go down here, we can affect things like the active parameter, animated, deforming, sleeping, linear thresholds, angular thresholds, all kinds of fun things. Even speed limits, so we can say speed min, max, etc. And this all correlates with the attributes that the bullet solver knows how to read and how to interpret. For more on that, check out my course Destruction 1 where I talk about all this stuff in detail. For now, let's just go to the physical attributes here. We have a lot of great presets which correlate with the density of various materials. So here we have concretes, and we can choose what kind of concrete that we'd like to use for the mass. In this case, let's go for a limestone. And we can even say dry and clean surfaces or lubricated and greasy surfaces. This all goes to affect friction, mass, bounce, and all kinds of fun things. So these presets are great because somebody's already gone ahead and figured out what makes sense for these particular types of material in the real world, and that'll give you a mass that's physically accurate to what that might be. All right, so the RBD configure will configure the attributes as it goes into the RBD bullet solver, and we also have RBD constraint properties as well. So if you ever want to alter constraint properties or you want to apply the attributes associated with constraints, so like let's say we did a connect adjacent pieces, which gives us the polylines, but we want to add all the attributes to that. This is what the RBD constraints properties will do. It'll basically go through all these polylines and add in the primitive attributes that need to happen. You can see this here with the null. There we go. So it adds things like the constraint name, constraint type, the strength, propagation rate, all that kind of stuff, so that you don't have to make a primitive wrangle and set it up manually every single time. So anyway, we also have that. That's all good. But for right now, we have everything we need to continue on with this RBD bullet solve. What I'd like to do is something fun where we basically have this magical effect that tears away at the top of this pillar. So we're going to have chunks begin to fly out in all sorts of directions like this, right? And as it flies out, I want to have the pieces fly around the scene like this in all sorts of crazy directions, and that can be controlled by a curve that we draw out. So I've already drawn out this curve ahead of time, and I made that into a separate geo network right here. Once we have the curve, the next step is to go inside the RBD bullet solver and create a pop curve force, which will bring in that curve and essentially create a wind tunnel that will push the pieces along the direction of that curve. So if we go up here, we can find the curve. And at first, it's going to be crazy like that. Let's go to the guides and first of all, take the guide spacing up a little bit so that we have less resolution there. And then also take the max influence radius and bring that down so that we have something a bit more reasonable like that. Okay, so we have that going on. Turn up the follow scale and the suction scale. The follow is going to bring the pieces along the direction of that curve. The suction keeps the pieces towards the center of that curve. So now as we go forward, nothing really happens. And we can try to go up here to the primary strength and turn that to, let's say, 1. And if we go forward, that will actually break apart like so. And now everything is flying around as you might imagine it would. However, let's say that I want to keep this thing on the ground. Well, the nice thing is that with this RBD configure, I can actually specify this active attribute right here, and I could set it so that the bottom pieces never actually leave the ground. So to do that, I could say, let's take our group and say at position.y. If that is less than a value of 0.5, then I'm going to alter the active attribute and set that to 0. So now in the RBD bullet solver, if I want to see this, I can go to Visualize and check on the Show Active. Here's the pieces that are active, and below that are the non-active pieces. So these guys won't fly away. Now, as I go forward, we have a problem. And that is, for some reason, now these guys aren't going to be able to fly. And to tell you the truth, guys, I'm not really sure why this happens. I've been trying to figure out why something that's active like this would do so. And it's also not sleeping. But truth be told, I think it might be a bug or something that I'm missing. But either way, it's not really the effect that we want anyway. We want to control the top going down. So we want to be able to break our constraints up here and animate all the way down so that over time we can control how quickly this erodes away the top portion of the column. So even though we have that sort of buggy sort of behavior happening, let's go ahead and just take our primary strength back to the defaults here of 10,000. And instead, I'm going to go to the constraint section right here, breaking thresholds, and we can check on this overwrite with SOP. And what this will do is it'll update these constraints on every single step based on what's happening here in SOPs. So what that means is that if I create a group and I group the constraints, let's call this our constraints break, like so, turn off base group, and then turn on keep in bounding regions. I can just animate this bounding box so that it covers the whole pillar like that. And anything that ends up in the group can be blasted away. So set a keyframe, Alt left mouse on the center. And then let's say at frame 48, we cover this whole thing and all the constraints are now broken. So we do that, and then we just set up a blast node, which takes advantage of that group. So now if we look at SOPs, we delete our constraints by doing that. And if we plug that into the constraints geometry like that, and we also have, again, this overwrite with SOP checked, then that should be able to remove the constraints manually. So now as we go forward, we end up with something just like that. And from here, all you need to do is play around with the different pop forces to get interesting results. So with the pop curve force, I decided to animate some of these parameters and just kind of overlap those areas. So if I show the guide geometry, it's kind of a big mess, but that's cool because then I have different streams of air pushing these particles in different directions, and it kind of gives a more dynamic effect because all these different pieces are following different paths. So I did that along with a pop force, which is just a curl noise, and that gave us the final effect. Anyway, I hope you enjoyed these lessons. I'm going to finish making the rest of the course very soon, and you'll find that at cgforge.com. Again, if you want to play around with the scene files that you see right here, you have that along with access to Destruction 1 in case any of that was confusing. Until then, take care, and I hope you have a great day.